So in the last class, we had ended until tube drawing, right? So we have seen how larger cross sections in tubes are converted into smaller cross sections, and that's what you call tube drawing, right? And we had seen that there are basically four different what do you call methods to do it. Like for example, yes, three different, not four. The first one, this is rod drawing, right, where you have a solid rod. So this is not a category of tube drawing, because tubes are hollow by definition. So rods are solid. How do you convert the solid cross section to, a larger cross section to a smaller cross section? If that load is applied at the end, right, then this would allow the rod to take the shape of the die cavity, right? I mean, the die is reducing in cross section, and therefore the rod has to accommodate that shape, and therefore the material is redistributed. But in case of tubes, you have a hollow, what do you call it? It's hollow inside, right? So how do we go about reducing the cross section of a tube? Then we use mandrels, as we have seen in the last class. Basically, with fixed mandrel, right? Without the mandrel, right? Wherein just the pulling force is applied. Here, the pulling, along with the pulling force, you also have a fixed mandrel, in the sense that mandrel will not move, but it is attached to some source, right? Fixed in place. Now here, with the floating mandrel, it's just in the air. So basically, that pulling force is what will hold the mandrel in place as the tube is passing through the die, right? So that's what we had looked at, and we've even looked at that video. Now, what are some of the other sheet metal forming processes on the presses, right? That is achieved using presses. So other sheet metal forming operations performed on conventional presses, right? Now, and then operations performed with metal tooling and flexible rubber tooling. We'll see just a glimpse of it. As for example, the ironing, right? We had covered some part of it in the last few classes, I think. That basically you have smoothening or making the wall thickness homogeneous, or constant wall thickness, if you want to call it. So more uniform wall thickness, right? Makes wall thickness of cylindrical cup more uniform. Examples of beverage cans and artillery shells. So, for example, that first example that we had seen, the flow. All the different steps that are performed to achieve that beverage can, right from a simple flat sheet to a beverage can, right? So one of the processes involved is also ironing, because you have to make the wall thickness uniform at some point, where after some processes you would have a non-uniform cross section. How do you make it uniform? So using ironing, we can make it uniform. Here you can see how is it trying to achieve a uniform cross section, right, within paper die. This is the start of the process, right? And once it goes through the die, this is during the process. Thinning and elongation of walls happening here from a higher wall thickness to a lower wall thickness, a more uniform wall thickness, if you want to call it, right? Because we are trying to achieve a constant thickness throughout. That is one desired output. And here BNF denotes the velocity with which that punch is moving and the force that is being applied, right? So artillery shells, even shells, a shell by definition is hollow, right? So that punch will go inside that shell and then try to make that wall thickness uniform. This is another process, right? A very common one in aerospace industry. that they use this rubber pad, and there is a foam block, or basically you can see this is kind of a support, right, or backing, because once that rubber pad touches this sheet, the sheet will have to take the shape of this foam block because of uh, the pressure from the rubber pad, right? So that sheet, as you can see, is taking the shape of that. The profile of that foam block is now upon that sheet. So this is another kind of process, right? Urine process. Before and after this, as I said in the last slide, your V and F indicates the motion and applied for respectively. Basically, V motion of the punch here, right? And of course, force that is exerted, or you can say it's a reaction from the sheet, etc. So therefore, this is another kind of forming process wherein you convert flat sheets into some kind of profile that you have on the foam block. And because the rubber is used, it kind of serves as a medium to exert pressure uniformly, right? Your uniform pressure is exerted, and therefore that leads to a more safer operation in one sense, and it also helps us to achieve better surface roughness in that sense, because there is no contact, as you can observe. The rubber pad, of course, yes, it will have, but it is not more of metal to metal contact, right? So that would a good surface finish is one advantage of this kind of process of working, right? And so that rubber pad plays an important role, we can say, in this process, in trying to shape it uniformly and without much friction, right? And therefore the surface roughness, better surface roughness. Now, what are the advantages of this Fourier process? As you have said, low tooling costs, right? Because the tooling that is involved in conventional presses is quite expensive, right? More number of parts, etc. The low tooling cost. Foam block can be made of wood, plastic, or other materials that are easy to shape. So, because that contour of the sheet depends on the foam block. So, how do you make? How easy is it to make that foam block is another uh, factor that will affect the economics of the process. So it can be made of wood, plastic, or other materials that are easy to shape. So if that is easy to shape, then it becomes easy for us to form different shapes with the setup. Rubber band can be used with different foam blocks, right? So the same rubber band can be used with different forms, right? Need not, you see, for example, in our general cases, we had to have same profile on the die and the punch, so that you would have that profile. You can say kind of simulated, or the profile is now imprinted, right, on that sheet. So here the rubber pad can be used with different form blocks, and as we had already discussed, form blocks are easy to shape, etc. It kind of goes from one point to another, right? So rubber pad can be used with different form blocks. Form blocks, although it's changing, rubber band need not change, so therefore you have less of a changeover if you see it that way. The changeover in the setup, right? For different profiles that are to be printed, or different sheets that have to be formed, yeah, with a specific shape or contour. Process attractive in small quantity production, right? So not much suitable for large or mass production. Attractive in small quantity production, and would more serve uh, more useful for batch type of production industries, smaller scale, medium scale industries, right? Now, as for the presses, right, because we are doing it in on different presses, what are those? I mean, what are the different main components, if you want to call, of those press frames? Gap frame, configuration of the letter C, and operator to a C frame. So, if you might have observed the frame of the machine tools, uh, they're basically of the letter C. So, straight-sided frame, box-like construction for higher tonnage. So that if not for C, right, you have this straight-sided frame. We'll see in one of the images that we have in the next slide. That looks like a box-like construction for higher tonnage, in the sense you are. It indicates the capability of the press, right, and therefore the press frame to take more loads, the right capability of handling higher loads, etc. You see, this is a gap frame press for sheet metal working. Capacity usually either measured in tons or kilonewtons, usually in tons, right? That's standard in the industry. That you see them as 100 tons, 150 tons, 200 ton presses. Depending on, it basically says the amount of force that it can exert, right? The maximum force that it can exert, and that is 150 tons in this case, which is quite a lot. But yes, it does require such kind of forces. Why? Because we are dealing with metals, right? Not plastics or any other material. We're dealing with metals, so therefore, to deform them plastically would require a lot of force, mechanical force. That mechanical force is of course coming from the press, so that would help us to form, right, sheet metal. So press brake with a bed width of 9.15 meters. So basically, it depends on either there are multiple dies or die punch setups, right? So in one stroke, you are able to form different components, right? Just with one stroke, it is able to form different components at different spots, right? Or it could be that you may have a long piece, right? So it could even be so designed that it can have that configuration. So the capacity here is 1250 tons. So this is basically a bending one. You can see here, two workers are positioning plate stock for bending. Here is one worker, here is another one. So to bend that stock, right? That's what we call them. So they're positioning the plate stock for bending, right? So these are taken from the industries which are having what we call larger machine tools. They deal with production, right? Several sheet metal parts produced on a turret press, right? All these are components, not parts of a turret. These are components made through a turret press, right? Showing variety of the hole shapes possible, as you can see, right from smaller holes, as you can see here, up until the large and the larger holes. Slots, if you observe, this is not a straight slot, right? A kind of curvy slot is possible, and you can see the amount of space it is left here, because once you press or try to take out the material here, and the next here you are having a lesser gap in the two, so that would it will not be that easy to create that. You have to have a system wherein there's some supporting below this that has to be perfectly aligned, right? The clearance values and tolerance values have to be uh, decided accordingly, so that this middle portion is not removed, because this is very susceptible to bending or failure when there are uh, material two sections which are being removed. So that is also another aspect that needs to be looked at. And what else? Yes, you have these more curvy slots. You have the holes, pattern of holes if you observe, right from circular, rectangular, right, square, and of course we have looked at bigger holes here, etc. And the different holes that are required, right? So all these are required, whatever we have studied, the processes, they're required to create consumer, what do you call, you have these sheet metal used in consumer appliances, you have it used in your automobile industry, right? All those industries you are having, I mean, you need such kind of capability that it can give out parts faster, and also with uh, care, like for example here as we have talked about, without what do you call, damaging the sheet for the surface roughness. Another thing is computer numerical control turret press, CNC turret press. Photovirtue of strip it, right? As you can see here, you have this controls set up here, right, which is used to program this, right? Computer numerical control. This is common word in CAD CAM, right? The one specialization of mechanical engineering is CAD CAM. So you are using computers, CAD CAM, computer aided design, computer aided manufacturing. So you're using computers to guide machine tools, right? That's what makes them to call computer numerical control, right? And they are used to control different presses. For example, here the turret press, they're even used to program or control lathes, right? I mean, basically that those are called CNC machines nowadays. That and several sheet metal forming processes, as we are discussing, and even those vending, right? Those also can be automated. And straight-sided frame press, as we have looked at a box-like configuration, right? Photography of Renard Press and Machine Company, as you can see. The console here is quite old, but still you have that controlling mechanism, right? Using these electronics, that this can be raised or lowered, and the amount of force that is required can also be set. Power and drive systems which are used, hydraulic presses, right? Very common. They use a large piston and the cylinder to drive the ram, because that is what is the what you required here. That using a large piston and cylinder to drive the ram. Basically, you, at one end, if you have the work at this end, let's say, this is your rod, right? Now you want to have some motion being given to this. How do you give motion? You attach it to this is your piston, right? So once that piston is fired up, just as your two-wheeler and four-wheeler, when you give fuel and you ignite it, right, using a spark plug, then this punch would mop up and down because of that motion that is given. So that in turn helps us to drive the ram, right? So the higher the piston volume is, the more power it can generate, right? Now, longer arm stroke than the mechanical types and suitable to debroil, right? Uh, Slower than the mechanical drives what we have looked at, right? So mechanical presses, they convert the rotation of motor to linear motion of ram, as we were discussing. Rotation of the motor, basically the motor rotates, but how do you capture that information and transmit it? You connect it to uh, just as, for example, piston assembly that converts the rotational motor to linear motion of ram, right? Rotation in the sense circular rotation is what we're talking about here, right? Basically, rotation itself is sufficient as a word. Now, high forces at the bottom of stroke suited to blanking and punching, right? Because in blanking and punching or piercing, you have this idea that the material has to be removed, right? So that requires uh, energy, and that would come. I mean, high forces at bottom of stroke is another point. So, as I said, because in punching and blanking, etc., require a lot of force at the end because that is where the process begins. So if that is not sheared off, then you will have issues, as for example in blanking and piercing. So if you take that into account, then we can have this understanding that why higher forces are at bottom of stroke are required. What sheet metal operations are not performed on presses? For example, stretch forming, right? Common example that is given. Stretch forming. These are not performed on presses, right? So then how do we do them? Let's see. What are those processes? First, stretch forming, there is roll bending and forming, right? Spinning as well. This is also important. And high energy rate forming processes. As the name suggests, they have a lot of energy at the beginning, or suddenly that energy is now exploded. So that's why it's given the name high energy rate forming processes, right? For example, stretch forming, right? The first example that we had mentioned was stretch forming. Now, the sheet metal is stretched and simultaneously bent to achieve the shape change. So you can see that the two ends, the jaws are keeping that in place, right? And then when that die is made to move up, right? Then you have sheets taking the shape of the die, right? So it is formed after stretching, right? That is one way to see it. Now, this is the startup process as we know. The formed die is pressed into the work with force F die, right? That is now inserted. So the startup process, the formed die is pressed into the work with force F die, right? As we know, causing it to be stretched and bent over the form. Where is F in your data set? Sorry. Yes. So once you give this what do you call the velocity, right, and then therefore the force, right? That's what the ultimate thing is here. But to start the operation, you have to give velocity here to this sponge, and then it would take the shape. I mean, it would make the sheet take the shape of this die, right? So then it causes it to be stretched, right? The force F die. This is basically the force that is uh, given by the die, but we can also say it is a force exerted by the what do you call the sheet on the die, because as we know, action is equal to reaction. So that's how we can say causing it to be stretched and bent over the form, right? F is a stretching force. As you can see, it is being stretched, right? That's why given the name stretch forming. Now, what are the forces required in the stretch forming, right? Because we are also looking at the different force requirements in those processes, right? The Sheetmetal processes. So that is given by L into T into YF. Very important to note what are all these things. F is a stretching force, as we know, that's what we are looking for. L is the length of sheet in direction perpendicular to stretching, right? So, right, perpendicular to stretching, if it is being stretched like this, the L is the length of sheet in direction perpendicular to stretching, right? So that is what, and instantaneous stock thickness. Basically, the thickness would be reducing, right, as it is formed. So what is the instantaneous, right? Any other instant, if you take while it is forming, the thickness is called instantaneous stock thickness, right? And YF is the flow stress of the work metal, and DF die force can be determined by balancing vertical force components, right? As we know, as per that action reaction example, we can have that die force. Now you see, because if what we are looking at is the force equation that is required in stretch forming. Now that length L, length of sheet in direction perpendicular to stretching. So if that L, what we are taking, right, is more, let's say, length of the sheet in direction perpendicular to stretching, so that increases, the force also increases, right? So that's what we are trying to verify, that how is it that when we increase or decrease the variables, what happens to the end function. So L is the length of sheet in direction perpendicular to stretching. T is the instantaneous stock thickness, right? At any instant, if you want to know the force required, then you have to put that instantaneous stock thickness, and YF is the flow stress of the work metal, right? So if you balance those units, YF is flow stress, basically Newton per mm square, let's say, then T thickness would also be in mm if you're looking for mm, and other thing is L is also in mm because it's a length. So mm square into Newton per mm square, therefore that we cancel and you get F. So that's how we get that force, right, when it comes to stretch force. As for roll bending, right, this is another process wherein large metal sheets and plates are formed into curved sections using roll. As you might have observed, that the sheets are made to undergo compressive stresses, right? And therefore that is helping us to shape that sheet metal, right? Large metal sheets and plates are formed into curved sections using rolls, right? As we are seeing here, these are all rolls. They're rotating, and therefore this rotation causes the sheet, because of the friction, the the rolls are now exerting force on these sheets, and therefore it also making that sheet to go outside once it is formed. So this is how roll bending can be helpful, because we are now using mechanical setup like rolls to manipulate the, or what do you call, modify the shape of this sheet metal. It is earlier flat. Now we want to give it some shape, right? Maybe a curvy shape is required for all intents and purposes. So that will get us to have that bent, what do you call, sheet. So this process is called roll bending. As for roll forming, very similar, but here you have different, what do you call, die setup at different points, and therefore this would help us to progressively make some component, right? Some sheetmetal component that we are looking for. So continuous bending process in which opposing rolls produce long section of formed shapes from coil or strip stock, right? So as the name says, it's continuous bending, right? Multiple die setups, as you can see, 1, 2, and 3 here, right? So the opposing rolls would produce this long section. So if they are what do you call, kept, as you can see, one on top of the other, the sheet would go inside it, and if it is forced to take the shape of that die, right, and therefore it will help us to get that final shape with progressive steps, right? Okay. So this indicates the roll forming of a continuous channel section. You have straight rolls, right? As you can see here, we are basically looking at it from the side, if you want to call it that way. If you're looking at from here, right, then what we will see is these things that will look at the process actually happening, right? And if it is this first one, this is straight rolls, so no other bending is required. The rolls are to be straight. Second one is the partial form, and the third one is the final form, right? So how do you go from one step to another? Basically progressively forming it instead of one impact that may lead to fracture and what do you call, waste of material, etc. How do we